Hey everyone, welcome back to Play Pause It again. Tonight we're going to be looking a little bit more at exponential functions, and I've titled this Part 1, an introduction. I know we kind of started modeling with exponential functions yesterday, but that was just us trying to get ourselves to start thinking about a different type of function. Today we're going to get a little bit more into the specifics of what makes something an exponential function and how it looks on a graph. So I'm going to start off by calling your attention to the equation y equals a times b to the x. And this equation, y equals a times b to the x, is the general form that we write exponential functions in. And yesterday, you started seeing some examples of that. When we were working on on last night's play posit, we were looking at some sequences, something like 4, 8, 16. And you were able to tell me what the constant ratio was, what were we multiplying by each time, in this case times 2, and what the zero term was by dividing by 2, and that got us back to 2 as our zero term. We ended up being able to write a rule that looked like y equals, starting at 2, multiplied by 2 to the power of x. And really what I want us to think about is what this a and what this b stands for. So this a, which is our zero term, stands for our y-intercept. And this b is the number that we're multiplying by. It's our constant ratio. And we're not going to call it a rate of change because a rate of change kind of implies that addition or subtraction pattern. So we're calling this a constant ratio. It's the number that we're going to multiply by over and over and over again in a sequence. This x on the top right here is our variable, and it's where we will input our domains, our input values. So I want to take a look at a couple of questions with you guys right now and just start kind of identifying and understanding where these things are in some different examples. So take a look at this example right here. And for right now, we're going to skip this. We'll come back there in just a moment. I just want you to look at this equation. F of x equals 1/3 times 6 to the power of x. And I want you to identify, for me, what the y-intercept of this function would be. Cool. So the y-intercept is this initial term right here. This is our y-intercept. And what is our common ratio here? Right. So our common ratio is 6. If I had to think about what this might look like on an input-output chart with x's and f of x's, if I plugged in the number 0, put in 0 right here, 6 to the power of 0, anything to the power of 0 is equal to 1. And 1 times 1/3 would just stay 1/3. If I were to plug in the number 1 to this function, 6 to the power of 1 is 6. And 6 times 1/3 means 6 times 1, which is 6, divided by 3, which is 2. And if I plugged in the number 2 for my x right here, that would give me 6 to the power of 2, which is 36, times 1/3. Put that 1/3 there. Times 1/3. 36 times 1 is 36, divided by 3 is 12. And we could go on and on and on here, and hopefully we've already started to notice a little bit of a pattern. From 1/3 to 2, I had to multiply by 6, and from 2 to 12, I had to multiply by 6. And so if I was going to look for input 3, I could also multiply by 6 here, and I would get 36, and so on and so forth. Cool. So take a look at this one for me. I'd like you to take a moment right now to tell me everything you can that's true about this function. Cool. So some things that are true. The y-intercept is 10. That's true. The common ratio is 2. That's true. Because the y-intercept is 10, when we input a 0 into this function, x and f of x, when we input 0, we're going to get 2 to the 0 power. 2 to the 0 power is 1. Anything to the power of 0 is 1. And 1 times 10 is 10. When we input 5 into this function, we get 2 to the power of 5. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And we multiply that by our y-intercept of 10, and we get 320. This exponential function is growing pretty quickly. So another thing we know is that it's growing. It's multiplying by a number that's getting it bigger and bigger and bigger. Alrighty. Let's go ahead and take a look at, we're going to go ahead and take a look at the graph of an exponential function here. So using the same words we used a moment ago, we know that 4 is our y-intercept, and we know that 2 is our common ratio. Common ratio. Cool. And because 4 is our y-intercept, we know that there's going to be a point on 4. And we really could think about a little input-output chart here if we wanted to. When we input 0, we get out 4. When we input 1, we get 2 to the first power, which is 2, and 2 times 4 is 8. So the next output after 4 is going to be 8. Input 1, output 8. And the next one, when I input 2, since I'm multiplying by 2, since my common ratio is 2, and I had an output of 8, my next output is going to be 16. And that's going to continue to grow very, very quickly. It's going to go off the page by the next point. We also need to think about coming backwards a little bit. If we followed this pattern backwards, we went from 16 to 8 to 4. The next output would be 2, and then 1, and then half of that is half, and half of that is a fourth, and half of that is an eighth, and we're going to get closer and closer and closer down to the x-axis, but we're never going to reach the x-axis. And that is because exponential functions have something called an asymptote. Asymptote. And an asymptote is an imaginary line that a function can never cross. In this case, no matter how many times we multiply or divide by 2, I'm never going to get to 0. I'm never going to get an output of 0. So there's this imaginary line along the x-axis right here called an asymptote, and my function's never going to cross that line. It's always going to be in the positive part of my graph. So I'm just going to sketch this graph in real quickly so you can see what an exponential function looks like. Something like that. And this function, because it's growing, because it's getting bigger and bigger and bigger, is known as exponential growth. Exponential growth. One other graph I want us to take a look at. Right here. And this function also has a y-intercept at 4. But the growth factor, or the common ratio here, is actually just a half. And that means, if I kind of look at my inputs and my outputs here, when I input 1, half to the first power stays half. And half of 4 is 2. And half of that is 1. And half of that is half. And so in this case, my outputs are actually getting smaller, from 4 to 2 to 1 to half, 1/4, etc. And if we follow this pattern backwards, so we go from 1 to 2, it's times 2. From 2 to 4, it's times 2. From 4 to 8, from 8 to 16, etc. This looks very similar to the graph we graphed a moment ago, but instead of being exponential growth, instead of growing exponentially, this function is decaying exponentially. It's getting smaller and smaller and smaller. Again, it will never reach 0 because no matter how many times I take half of something, half, 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 it's going to get smaller and smaller and smaller, but it's never going to go away completely. So we still have an asymptote. And my exponential function should look something like that. And that is exponential decay, because it's getting smaller and smaller and smaller. Cool. All right, last thing for us to think about is I would like for us to write our own equation here. So I'm going to give you a moment to think about this. We need to know what the growth factor or the common ratio is. And we need to know what the y-intercept or the 0 term is. So think about those two things for this question, and then we'll answer it together. Cool. So it would appear that the common ratio here is times 4. And to kind of go back to my 0 term, I'd have to go back through my 2 and my 1 and my 0 right here. And so if I divide by 4, 16 divided by 4 is 4. And if I divide by 4 again, I'm going to get back to 1. And if I divide by 4 again, I'm going to get to 1. So we've got our 0 term, and we've got our growth factor. Now, how are we going to put those together to write an equation? Cool. So the way we write these equations is f of x equals, we're starting with our y-intercept, which is 1/4. We're multiplying that number by 4, and we're doing that x amount of times. Before we go, I'm wondering if you can tell me whether this is exponential growth or exponential decay, and why you think that. Alrighty, so just to kind of go over really quickly, this is exponential growth. Even though it's starting with a very small number like 1/4, starting with a fraction, what we're multiplying by each time is 4. And every time I multiply by 4, my output gets bigger and bigger and bigger. That will make this exponential growth. So this video, I know, is pretty long for a play pause it, but hopefully you took some really good notes, and we'll be ready to talk about this some more in class tomorrow. Bye, guys.